Hello, welcome to today's further maths video. But what are we trying to do today? Well, I usually like to try and have a bit of intrigue and mystery when I'm introducing a topic, but unfortunately, in the format of a video, it's always slightly spoiled by the title. So therefore, you're probably well aware that we're looking at simultaneous equations, which I'm expecting you to actually already be able to know how to solve. You could, of course, rearrange one of the equations to make it x equals or y equals, and then substitute that into the other equation to eliminate it, then leading you to get one equation with one variable, and then once you found that value, you can find the other variable as well. But what happens if we want to speed this process up, or even better, get a computer or calculator to solve it for us? Well, it all comes down to matrices, because you can express a linear system of equations as a matrix equation. All you've got to do is look at the coefficients of the x's and y's like we've got here and write that as a square matrix. So in this case, we'd have the matrix 2, 3 for the coefficients of the first equation, and then the coefficients of the second equation would lead to the next row in the matrix, so minus 4 and 11. If we multiply that by the 2 by 1 matrix xy, of course, that means if you multiply these two matrices together, you are going to get a 2x plus 3y and a minus 4x plus 11y, due to the fact when multiplying matrices, you always get the rows in the first matrix being multiplied by the columns in the second matrix. And therefore, that must be equal to the matrix 1393. But why was this helpful? Well, the thing to note is that we are trying to find the values of x and y, and conveniently, those variables are in their own individual matrix, which means it's possible for us to isolate them if all we do is rearrange this matrix equation. We effectively need to get rid of that matrix of 2, 3, minus 4, 11, that 2 by 2 matrix, from that left-hand side to rearrange it to move it across to the other side. And the good news is we can do that because it's being multiplied, so therefore all we have to do to undo it, inverted commas, is multiply both sides of the equation by the inverse of that 2 by 2 matrix. Because the 2 by 2 matrix is in front of the xy, in order to make sure the inverse is cancelling out that 2 by 2 matrix, we need to multiply the front of both sides by the inverse. So therefore we're going to do 2, 3 minus 4, 11 inverse times by 2, 3 minus 4, 11. Lots of x, y. And on the right-hand side, as we multiply the left-hand side at the front by the inverse matrix, we've got to do the same thing to both sides, because that's always the rule with equations. Whatever you do to one side, you've got to do the same thing to the other one. Of course, the 2 by 2 matrix and its inverse will cancel out on the left-hand side, meaning we're just going to be left with xy being equal to that inverse matrix multiplied by our 1393. Luckily, that would be very easy to find, either manually or, as we live in the modern times, through the wonders of modern technology with calculators. So if you just plug that all into your calculator, you will get minus 4, 7 as a 2 by 1 matrix. That therefore tells us that the answers are x equals minus 4, y equals 7, and boom, we're done. The only thing you're probably wondering is, why would I want to do this, considering I already know how to solve simultaneous equations? But guess what, folks? This stuff works in 3D too. If we've got 3 simultaneous equations with 3 variables, we can use matrices to solve this stuff too. And although this system of equations could still be solved using a similar method to what we usually use for 2 variable simultaneous equations, the time efficiencies we'll make by using matrices will make it definitely worthwhile to do it this particular way. So therefore, all we've got to do is write the coefficients as a 3 by 3 matrix this time. Realize that's still just being multiplied by, well, this time x, y, z, because of the fact we got that third variable, again because rows in the first matrix times by the columns in that second matrix will get us the equations in the format we're used to seeing, and then the right hand side of the matrix equation is those constant values that were already on the other side in the original equations. Therefore, all we've got to do to solve this equation is multiply the front of both sides by the inverse of that 3 by 3 matrix. Therefore, meaning you'll end up getting x, y, z is equal to 1 minus 10, 2, 5, 3, 8, 2, 4, minus 7, inverse, times by minus 15, 29, 7. And that's again just something you can instantly type into the calculator to very, very quickly get this as your matrix answer, leading to a final answer of x equals 3, y equals 2, and z equals 1. And I'll tell you what, that's really cool, partly because this is an idea that could be scaled up to even bigger dimensions. Of course, the bigger the dimension, even after a while, your calculator will struggle with finding the inverse of that, but it's something that can be done, and definitely much quicker than solving these things manually. But on top of all of that, for those of you studying this content in England for A-level, you might need to know for some exam boards how to solve a particular type of question that looks like this. Basically what they'll do is give you a really wordy context-based question, and the thing is they are questions that sometimes freak some students out just because they're faced with all these words and it's not immediately clear, certainly for most of the words, what sort of question or what sort of area of maths we're dealing with. It's only when you get to the very end of the wording where it says form and solve a matrix equation, you maybe start to twig, oh, this is ultimately just going to be that simultaneous equation stuff we were looking at, but using matrices in order to do it. The advice I'd give for these questions is the same advice I ultimately give for all heavily worded questions, which is to take it one sentence at a time, breaking it down to extract all the key information you need from the words to ensure you don't miss out any key information along the way. So don't let your eyes just instantly get drawn to the numbers because you might miss some information along the way hidden in the words. So in this question, it starts by mentioning a stationery shop's 3 biggest selling items in stock are notepads, pens, and staples. Okay, now it's mentioning some things, it's mentioning different categories of things, and basically the fact that there's numbers of boxes of these things. That is the thing we're going to be measuring this question, and after a very quick scan through the rest of the question, you'll notice that they haven't given any variables for those numbers. So as always with wordy based questions, if they don't tell you what the names of the variables representing the things are, then you have to decide what they are yourself. But as you're the one deciding them, then you have to let the reader of your work, in other words the examiner, know what you are choosing as your variables for each category. So obviously there'll be some questions where they do that for you, in which case, you know, the classic example of that is they'll write the variable letter in brackets next to each word as they go. But if they're not doing that, then you do have to define it, and there will often be a mark awarded for doing so. So if you don't do it, you're probably going to lose that mark. So one way of doing that would be to start the question by saying, let the number of boxes of notepads be n, let the number of boxes of pens be p, etc, etc. However, I can understand why some students feel a bit lazy about doing that because you have to write out all these sentences, but I'm still going to write them out, and that's because I want to show you that if you are somebody who doesn't like doing unnecessary work, you can at least make some efficiencies by how you choose to do this wording by saving having to write the same stuff repeatedly. For instance, you could say let the number of boxes of, and then if you put a colon, what this allows us to do is then be really cheeky and just use bullet points by going notepads be n, pens be p, and we could say staples is s, but I'm not going to because S is an annoying letter to use in maths because it looks so much like a 5, or at least it does if you have terrible handwriting like me. So I'm going to randomly use the letter Q for no apparent reason because that's the whole point. We're defining the variables, we're allowed to do it. Free world. So there we go. That's the first bit of the question done. But then we need to extract from the words what the simultaneous equations themselves are going to be. So crucially, we're told that in January, there were a total of 1,655 boxes. So that means the number of boxes of each category all added together must total 1,655. I could also update my wording as well, because now I'm realizing I maybe want to make the variables I have specify the number of boxes in January. So therefore, once we've done that, we can now say n plus p plus q equals 1,655. That was the total of boxes that they'd said were there in January. Then traveling on to the next part of the sentence, because that gives us more information leading to another equation, because they tell us there were 105 more boxes of staples than pens. Now you've got to be really careful with these sort of wordings, because students obviously realize it's something to do with adding or taking away, and the number 105 is clearly important, but commonly people will put the 105 in the wrong place. So therefore I want to highlight, because it's saying there's 105 more boxes of staples, the staples is the bigger quantity. So therefore that implies if you want to do it by writing it with an addition, then you're saying you've got to take the boxes of pens, add an extra 105 onto it to get the number of staples. So therefore we're going to have P plus 105 equals Q. Continuing on with the wording, we're then told that now at a later time by the following September, due to the items being bought and sold, the number of boxes of notepads has now increased by 19%. That means if we are doing this as a percentage increase, we are effectively multiplying by the number 1.19. That would mean we'll have the 100% we had before plus the extra 19%. But the thing is, we don't know how many we had before, but we do have a letter representing it. So therefore, this individual sentence here is telling us that we now have not just n number of boxes of notepads, we have 1.19n boxes of notepads. We also then in the next sentence are told that the number of boxes of pens has increased by 0.8%. Now watch out as soon as they do things like this, because we're already having to convert percentages to decimals, and ultimately I know you're good mathematicians if you're watching this video, but it's the little silly mistakes you need to watch out for. Do not make the mistake of writing 1.08. Of course it would be 1.008, and that would be P. And then on the third bullet point it says the number of boxes of staples has decreased by 15%. And that's really important to highlight, because again, really easy to make a silly mistake there. People will just get in the habit after the previous two bullet points lull you into a false sense of security of always just adding the decimal that's said in the question onto 1, but as it's decreased this time, we've got to take it away from 1. So it's going to be 1 take away 0.15, which would be 0.85 instead, because it says that word decreased. And then the overall number of boxes has increased by 83 boxes. Again, people make the mistake of the equation we're about to write just setting that equal to 83. But no, it's telling us that the number of boxes we already had before, we're then adding an extra 83 on top of that. So therefore, we need to do the 1655 we had before plus 83, which, by the way, would get you 1,738. So that leads to the third equation being 1.19n plus 1.008p plus 0.85q is going to equal 1738. Cool, we've now got 3 simultaneous equations. We now need to solve them using matrices. Worth acknowledging that although you could technically solve these equations manually, because the question specifically asked us to do it by forming and solving a matrix equation, if you did solve them manually without using matrices, you would lose all the marks probably. So therefore, be careful for that. Anyway, you'd want to do it using matrices either way, because it speeds up the process if you've got a calculator. Thing to be aware of is the fact that we want all the variables on the same side as each other. So actually we're going to rearrange that second equation. So therefore we're going to rearrange it to be minus p plus q equals 105. Taking away the p from both sides to move it away from that 105. That means we can write this system of equations as 1, 1, 1 for the coefficients in that first equation. Watch out, it's not got any ends in that second equation, so it's going to be a 0, then a -1, then a 1, and then 1.19, 1.008, and 0.85, followed by NPQ, and then that's going to equal the numbers 1655, 105, and 1738. Again, just like we showed before, you just got to multiply the front of both sides by the inverse of, in this case, that 3×3 matrix. Do be aware that you don't need to show technically that line of working where the inverse and the original matrix cancel out. You can just jump straight to having rearranged it in this way, but you do need to definitely show this step. So this step I'm writing out right now, I'd expect everybody to write out because it counts as the method. And if you were to type that into the calculator, that would lead to an answer of 800, 375, and 480. Now, another thing to watch out for is it'd be very tempting for a lot of students to just think they're done at this stage, but with context-based questions, it's always a good idea to put your answer back in context at the end. Not because they're necessarily always going to punish you if you don't do that, but there generally is at least a mark in each paper awarded for dealing with context-based questions in an appropriate way, like putting or relating your answer back to that original context. So better safe than sorry, even if you'll get away without doing it sometimes. So for the sake of this question, I'm going to say in January there were 800 boxes of notepads, 375 boxes of pens, and 480 boxes of staples. It takes time to write this out, but just this one little bit of extra effort is going to put you in a position where you're guaranteed to get the marks. You're not giving them any excuse to be like, no, you didn't do this. So that's always a good idea. Sorry I've crammed it in at the bottom there, but because I said it verbally, you would have heard, even if you can't see it properly, what I've written there. So there you go. And with all that said, we're done for today's video. Hopefully you found today's video useful, and it's also quite interesting because it shows the power and the role that computers can have in helping us do various levels or parts of pure maths. See you in a future video. Goodbye.